Welcome to today's episode. Today, we have a special guest with us. We have the privilege of talking to the EMP doctor, author, and also NASA scientist, Dr. Arthur Bradley. Welcome.
Thank you. Thank you for having me on.
So, Dr. Bradley, let's first talk about your background and expertise in your field of study.
Sure. Yeah. So I've been an electrical engineer since long time, 1990 or so a long, long time. I've been with NASA for just over 20 years. I'm here in Virginia. And my day job is to typically design and build electronic systems. I've been doing that both in and out of NASA for a long time. In terms of electromagnetics, which is what EMP would fall under, I'm one of the handful of people who are certified within the agency to actually call themselves an EMC engineer, which I am. And so I'm typically called in to solve difficult electromagnetic problems where you have noise coupling into systems, that kind of thing. And all that is kind of related to EMP and solar CME and things like that. So I've been around for 30 some odd years doing this kind of stuff. I've been involved with the EMP community, I don't know, maybe 15 years or so, working on unique products, running tests, trying to debunk myths that weren't really true, lots of stuff like that, because it's a complex field that a lot of people have opinions about, or maybe things don't make sense, and so I try and get involved and sort it all out. Do some private consulting for companies and government groups to help them harden facilities and equipment as well.
So, can you talk about your expertise and experience with NASA and how that relates to knowing EMP and solar flares and the safeguards that technology kind of revolves around that in your experience?
Sure. Yeah. So my job at NASA is not really related to EMP preparedness, and so I'm not here as a representative of NASA in any way. But with that said, there's a lot of overlap in that a lot of the work I do at NASA is related to electromagnetics. Particularly, like I said, let's say you're building a satellite system and you have to test it versus the mil standard 461, and maybe it starts to fail some of those tests where you induce high energy on it. They might call me in to help figure out how do we shield the system, or how do we make the system more robust, figure out where the coupling mechanisms are, things like that. It's not the only thing I do. I'm actually a manager at NASA, so I manage a whole group of electronics engineers and technicians. But I'm fortunate that I still get to keep one foot into the technical work, and I get called in on these difficult problems sometimes to solve, which is a lot of fun.
So, our channel is geared toward the automotive sector. And whether it's off-roading, overlanding, or bugging out because of a disaster or high altitude EMP, some type of black swan event, we need to think about ways to protect our mobility. And we have a lot of questions surrounding EMP devices, hence why we kind of wanted to pick your brain. Can you summarize what is a EMP and CME?
Sure, yeah, they're distinctly different things. Sometimes people get them mixed up. Let's talk about a CME first. That's a solar coronal mass ejection, which, of course, the sun is a big blob of, gaseous energy, and it sometimes spits off solar flares, it emits solar flares, or solar coronal mass ejections. And a coronal mass ejection is really just a big blob of plasma, which is a charged gas that comes off the sun, and they're huge, and so they flow through space, and most of the time they go in directions that don't affect us, and they don't make any difference to us. But every once in a while, they'll line up with the Earth, and it'll wash over the Earth, if you want to think about it like that, and that can perturbate the Earth's magnetic field lines, and it can cause some problems for communications and other things like that. So a solar CME is a very natural phenomenon. They happen all the time. Only once in a while they're really powerful. Maybe every 150 years the Earth might see a really powerful one hit the Earth. The last one we saw was something called the Carrington event way back in the 1800s. Everybody uses that as kind of a reference of, oh my gosh, we better not have one of those today or we're in real trouble. But that's what a solar CME is it's this big ejection of plasma from the sun. An EMP, go ahead if you had a question.
I was going to ask you, so have we seen anything that has happened recently that has caused that type of disruption, or have we not even experienced any type of CME that's really caused any chaos as of yet?
Yeah, we did have some. There are CMEs that hit the Earth, like there was an outage in Canada, northern U.S. A number of years back. I think it only lasted like 12 or 24 hours. It wasn't a big long-term thing, but it did show the effects of a CME. We have not had anything like a Carrington event hit the Earth since the 1800s. people worry about that because all the simulations show if that event hit the Earth today, you'd have widespread blackouts on most of the planet, and they could last for a very long time because the damage could be very substantial to some of the transformers that we use in power distribution. So the short answer is we've been pretty lucky, but like I said, it's about every 150 years they say you're due for one, and that was back in the 1860s, so we're a little past due for a big CME to hit the Earth. And the tricky part with CMEs is we know they're coming. They don't travel at the speed of light, unlike a solar flare. So we have satellites that monitor the sun, and we'll see a big blurb of plasma come off, and we'll go, oh, hey, there's a big thing, big CME coming your way. And then we'll radio ahead, and so we can get ahead of the CME and tell the Earth, hey, there's a big CME about to hit the Earth in the next 2 days. All right, it takes a couple of days. The problem is that nobody really knows what it's going to do to the Earth. It's very difficult, it's impossible to predict the effects of a CME, even a big CME. And so there's a lot of reluctance. Like a lot of people say, oh, well, if we see a big CME, we're okay because we'll just shut down the grid. And then, for the time that it comes over us, and then we'll bring back up the grid and we'll be okay. Well, there's a couple of problems with that. One is we don't know that CME is even going to be that big of a deal when it actually affects the Earth. We really don't know until, I was told, within about an hour of it happening. So it's kind of like real time. And then the other thing is, even bringing down the grid doesn't in any way guarantee that the grid is protected. It doesn't need energy in the grid distribution system to couple in that CME and cause damage to the transformers. So you'd have to throw disconnects where you're physically disconnected and isolating systems. And while some of that exists, it's not widespread, like we're prepared to disconnect major portions of the grid like that. So I don't even know that such a thing exists. Even if we wanted to protect the grid, there'd be limited things we could do. So anyway, that's the whole side of the CME, is that, yep, it's coming, guaranteed, almost guaranteed even in my lifetime, we're going to have a large CME hit the Earth. What it will do, we'll see. Nobody really knows. The other side's a very different thing. An EMP is not a natural phenomenon. It's hey, we're going to do some kind of a weapon, right? And the way they do it is they take a nuclear warhead up high into the atmosphere, hundreds of miles. They detonate it. That detonation essentially causes high energy release gamma rays that affect and perturbate. They ionize the air molecules, which just means they strip electrons off, and then those electrons spin around our magnetic field lines and they perturbate the magnetic field lines in a way that's kind of similar to a CME. So you can see there's some overlap, but in very different, distinct frequency regions. So an EMP has a very high frequency thing that perturbates the fields, and then kind of a moderate frequency range, and then a very slow low frequency effect, which the low frequency effect is very similar to a CME. Those two kind of correlate. But the EMP, unfortunately, also has this really high speed, nanosecond wide pulse, the electromagnetic pulse, and that pulse can couple into things that a CME could not. So it can couple into many more things besides the power grid. It can couple into your computers, your cell phones, your radios, any small scale electronics just about can be damaged by an EMP if it has solid state electronics in it. And so cars, planes, boats, satellites, all those things potentially could be damaged by an EMP.
Anything with conductive material inside of it.
Yeah, and the more modern the electronics, the smaller the gate size of the transistor, the more likely it is to be damaged. And so stuff that's old, in the 1970s, less likely to be damaged than, let's say, something built in 2024. But the short of it is anything with solid state electronics, computer chips, those kind of things, digital logic could be damaged by an EMP. And that's the E1 event that couples into everything, has potential to damage stuff. And then there's this E2 event, this medium frequency range event. That's kind of like a lightning event. It's really by itself not that dangerous because most of our systems already know how to handle a nearby lightning strike. Not a direct lightning strike, that's a whole different beast, right? But lightning hitting down, a half mile away and you get a big bzzz on your house wires, everything kind of generally knows how to tolerate that. On occasion you lose something, your TV goes out, but most of the time we survive it. Certainly cars can survive it. You can have a lightning strike hit the telephone pole beside your car and your car is still going to be able to go. Airplanes the same, right? Airplanes get hit by lightning directly. I've been in one that was hit by lightning, scary as all get out, but again, they keep going, right? They're robust enough for that kind of energy. And then there's this E3 event, this slowly building kind of thing, like a tide rising on the power lines that occur from an EMP as well. And that energy can flow down these long conductors that are distributed around the Earth. And that slow, low frequency energy is basically the same thing as a CME from the sun. That's what the CME does, is it generates this energy on these very long conductors. So one of the things I tell people is, if you want to distinguish between the two, they both can take out the power grid, right? That's unfortunate because that's the worst they're going to do anyway, but they both can do that. The difference is a CME really only does that. It only affects long, long conductors, things with miles and miles of wire. An EMP can affect just about everything, small things, big things, it doesn't matter. And so they're different, and the way you prepare for them is slightly different as well, all right? But anyway, so that's kind of the distinction between the two and how they work.
And how long has the study of these forces been researched?
Yeah, well, at least back to the early 60s. In 1961 and 62, there was a lot of testing done by the U.S. and Russia. U.S. had something called Operation Fishbowl, where my understanding of it, they were detonating high-altitude nuclear weapons, right? So they're detonating warheads. They were really looking to see if that was going to be a protection mechanism against incoming missiles. Could they disable incoming missiles with an EMP, which makes sense, right? And they had some unintentional side effects, things like Starfish Prime, where they detonated over the Pacific Ocean, and they saw hundreds of miles away damage to electronic systems on the ground. And then they realized, oh, wow, these EMP waves are really powerful. Maybe this could be an offensive weapon as well as a defensive weapon. And that's kind of where it's gone now. Every time you hear EMP nowadays, you're usually talking about an offensive weapon, something to destroy something, like a military base or even communication systems or whatever. So they've been around since the 60s, and Russia did something similar right around the same time, 61, 62. They detonated multiple warheads over Kazakhstan, which was a populated area, but they were up high, from tens to hundreds of kilometers, and they detonated just to see what would happen. Now keep in mind, the 1960s electrical power system was very different than ours today, right? And things have modernized, and yet they still did see some fires and some damage to these power plants and things like that. So the conclusion was, hey, this is a viable strategic weapon we could use. And today people feel like we're much more vulnerable because we have a lot of these what are called SCADAs, but they're these controllers that control everything, the switching of things and the distribution. And those things have been shown to be susceptible, particularly susceptible to an EMP. And so people think, yeah, that's probably where the enemy would go after, is they detonate over the central U.S. or over maybe one of the seaboards, and hopefully take out the grid, the interconnection systems, which could disrupt lots of things in the U.S. for a long period of time. And likewise, we have the same ideas of, if we had to attack Iran or Russia or China, I'm sure we have people planning where would we detonate things to cause a mass disruption of their military operations and things like that. That's kind of what we found.
One analogy that I like to think about it, because I feel like I understand E1, E2, E3 to a degree, and maybe you can correct me if I'm wrong, but a good analogy would be for it is if you were to throw a rock into a pond, and that first initial splash would be that E1, and then the ripples of that splash would be E2, and then the water hitting the shore and then reverberating back in where you can see ripples throughout the entire pond would be the E3. Would that be somewhat of a summary of the effect?
Seems like a reasonable analogy, sure. I tend to think of it in terms of like time duration, and that's kind of similar to what you're saying. Something occurs very quickly and then it's over, and then something kind of takes some time to occur, that's the E2, and then there's this long-term slow growing effect, which is the E3. So yeah, it seems reasonable.
Which E3 can be anywhere between, what, 6 to 8 hours, something like that, that the atmosphere
Yeah,
is
usually they say minutes to hours, but whether it's 5 minutes or an hour probably doesn't make a lot of difference. It's long enough that if you had protection mechanisms, you could switch them in. Unlike really even E1 or E2, E1's over in nanoseconds, 20 nanoseconds or something, so you're not going to do anything physical in that time. E2, yes, you can shunt energy away like we do with transient surge protectors and stuff, but that's a well-known, not a physical movement, but an electrical diversion tactic, right? And then E3, you actually have time to physically open switches and move things, right, and disconnect from grids and things like that. So different protection methods.
So regarding devices, what has been the evolution of the scientific process for designing devices against these forces?
Yeah, that's not a clear path, I would say. The effects of EMP have been known for a long time. And even, I think, knowledgeable people, let's say military people, they understood a long time ago how you would protect against them, right? If you have a powerful electromagnetic disturbance, It's just like any other electromagnetic wave. What do we do to protect against it? We can shield things, right? So if you can completely encapsulate something in a conductive barrier, you're essentially immune to the EMP, all right? Even a mediocre EMP barrier that's not perfect, you're going to be 99.99% field reduction. So you'll survive it, right? So you can cover a car, you can put your radio in a bag, a conductive bag. A lot of different ways if you can shield. So shielding, everybody has known for a long time, is like the best. That's the best you get because you're guaranteed protection. The trouble is a lot of our systems can't be really shielded because they have wires coming in and out. They're going to be plugged in, or they got data lines or whatever, right? And unlike what people think, you can't just have, let's say you have a radio and you drape a conductive cover over it, but your power wires are coming in and your data line, your antenna's going out, whatever. You've got ins and outs of it, but you've covered the radio body. It really doesn't do a lot for you because the energy just couples onto those wires and comes into the shielded space anyway, and then re-radiates or just couples into things from a conductive path. And so to do it right, you have to have a perfect conductive barrier, and anything that comes through that barrier has to be filtered, all right? Well, that people know how to do that. We build Faraday cages, we build Faraday rooms. I have one at work I use, and there's filters on the wall. Everything that comes in goes through the filters, and it does a wonderful job. So everybody knows in the industry how you would protect things. The difficulty is it's not cheap. It's not cheap at all to do that. A good Faraday cage room, the size of my little office here, might be $250,000 or something like that. They're not cheap, right? So you have to look for other methods to protect systems that are imperfect, but that are way better than nothing, right? And what we usually resort to is that things that can be shielded are shielded. So if it's small enough you can shield it by itself, no wires coming in and out, you shield it. If you can't shield it, then you try and identify the most likely path of energy into it, which is usually the power cord or the data cords, any kind of conductive cords. They're kind of like pipes for energy. They just bring in unwanted energy. So you can put transient protection devices across those lines that come in, or you can put ferrites, which are ways of suppressing the transient currents that flow down those wires. And indeed, you do greatly minimize the energy that might couple into that system from those conductive paths. All right, and I have some ferrites. I can show a couple of them. Like here's a big ferrite that might clip around a power cord to your computer or whatever. And I brought some different transient devices. Here's a small one that might go across the battery, for example. There's one that might plug into a cigarette lighter. You might have some too. Yeah, trap bees. Yeah. And there's lots of different ones. There's a little plug that might plug into like a generator and things. What are these things? They're not magic in any way. They're just transient, very fast transient reducing devices. So they turn on when the voltage gets too high, and they try and sink the energy away to ground. All right. So you put those in my method of protecting is you put as many of those distributed in your system as you can. Right now, if it's a small system, it may just be one thing on the power cord, but if it's complicated like a car, it has hundreds of controllers and all kinds of electronics in it. It's hard for me to believe or understand that I can place one thing in one location, let's say at the battery, a big box at the battery, and my entire vehicle is now protected. Well, that only makes sense if the battery is the source of the damage, right? And now I can sort of sink it at the source. But the truth of it is the energy is going to come into all of the cabling, all over the vehicle. And it's going to distribute up and start popping microcontrollers and computer chips throughout the vehicle. Now, near the battery may be protected because you've shunted that energy, but not necessarily everywhere else, right? So my thinking is, and my thought has been a long time, you want a distributed system as best as you can. In a perfect world, you'd place one every 3 feet around your vehicle into your electrical system. And indeed, the energy then would be sort of stapled at lots of places, right? It couldn't go above a certain level at lots of places. In reality, we can't get to our electrical system very well, right? There's only a few places you can easily tap into it, which is why we came up with like the trap that you can go in the cigarette lighter plug, right? Or across the battery, or ferrites on the power cord. We recently came up with an onboard diagnostics port one where you can plug into the OBD2 port. Again, you're just trying to get across the power lines to offer some transient protection so you don't get too high a voltage. And sure, we have, Faraday came up with a really nice heavy duty, it's a great product. The DEFCON vehicle is a fantastic product that if you want a really heavy duty surge protector, you can certainly put it across your battery, and it greatly helps minimize transients, but I don't think it fully replaces the distributed idea. I think you still need to think distributed. Even if you do all those things, though, what you're doing is you're buying down risk. I try and tell people this is not like wrapping your car in a conductive barrier where you know you're good. This is about trying to keep those transients that get coupled into your car down. And by doing it as many places as you can, you have a better chance of preventing damage to your systems. That's the goal. And that's the method we've gone after.
I'm all about analogies, and so I kind of think about this process as if you were to protect yourself while you're on the road. If you think about a motorist that's on a motorcycle that is not wearing a helmet and just flying down the road, his level of protection is literally minimal. Is very likely that he's going to get hurt in any kind of accident, and badly hurt probably. Now, if we put a level of protection like a helmet on that person or a protective jacket, they'll probably have a much higher reduction in burns from hitting the road, head injury, trauma to the head, because having the helmet is going to protect them. Now, if we take that same person and put that person inside of a very well protected vehicle, maybe with a roll cage, now we're even upping that level of protection even higher for that individual. And so what you're saying is that the more levels of protection that we're adding to a vehicle, just the more robust the amount or percentage of the likelihood that that vehicle is going to survive. And I would also assume that this would be dependent on the epicenter of where that blast or anything would come from. So if you were directly overhead, you could have several things on there, but you could have catastrophic damage to something if you're directly below it, as opposed to being further outside the circle of that epicenter, with having those same types of mitigation tools on your vehicle. So it's really going to depend on scenario based on location, but then also how much protection that you're adding, whether it's the trap devices, the shunt devices, and all the above in multiple locations, correct?
Yeah, that's right. And it's not even as simple as how close you are to the detonation. You end up with a weird like horseshoe pattern that develops from the highest fields around it. So you'd think it would be, circular, and the further out you go, the less it is. And to some degree it is that. But right near the detonation, let's say the 50, 100 miles in the area of the detonation on the ground, it creates a weird pattern, not like a horseshoe pattern is the way I describe it. So you could be, 2 miles away from somebody else and them happen to be inside that horseshoe area and you're outside and you suffer no damage and they suffer damage. So it's a tricky thing, and it's even more complicated than that because it depends on which car you have, how much metal your car, it has natural shielding, right? How the wires in your car are shielded or oriented versus the electromagnetic wave. And there's so many complexities to it. And so many people say, well, why don't we just design cars that are EMP hardened or something? And the reason is that every car would have a unique solution because they all have unique susceptibilities, right? And you really have to approach it, as an engineering problem when you first started on the vehicle. And honestly, the cost of that just is not, reasonable for a car manufacturer, I think. But yeah, so it certainly depends on where you are, and you're just buying down your risk that wherever you are, you have improved your chances.
Yeah, we work on vehicles every day, and we often find ourselves scratching our head why engineers decided to put some things in places that
Right.
they did,
Sure.
or maybe some things were an afterthought, and we're like, oh yeah, we needed this too, and then it just got stuck there,
Yeah.
and we end up having to fix it and it's buried location sometimes, and
Yeah.
so I totally understand the complexity of that because there are some cars that are engineered. It's like, wow, everything was thought of on this one, and then you go to the next car, and it's like nothing was thought
Yeah.
of. It seems like
Yeah.
this entire car was an argument. So.
Yeah.
Um, so moving on to our next question, I want to kind of discuss a little bit more in depth of these devices between the traps, ferrites, and shunts. You talked a little bit on those. What specifically, like that big robust DEFCON, what does that is a shunt, correct?
Yeah, so essentially it's going to have a limit to the max amount of voltage it will allow it to develop across its lines, and then it will shunt away the energy to ground, all right, to the car frame, which is essentially
To the chassis.
to chassis. Yeah. And so, you hook it up across the battery and over to chassis, and it has devices in it that will turn on when the voltage gets too high and drain that energy away. When it's not turning on, they really don't have any current through them at all. The only current in the device is just a little green light that's lit. So that's it.
And one way we can think about the energy that's being applied at that point when that device kicks on is, correct me if I'm wrong, is as heat. So that excess heat is being transferred into the chassis of the vehicle.
Well, it can turn into heat, certainly. Electrical energy easily turns into heat. Basically, if you flow a current through any kind of resistive material, it turns into heat and gets hot. And so certainly if we're dealing with high currents, you may see heat. But the reality of it is, in this case, you're shunting away energy before it has time to turn into heat a lot of times. So you're just taking direct electrical energy to chassis, as opposed to, let's say, shunting away a heat element, which is a little bit different, but they are related, right? And a good example of that is like the ferrite we mentioned. It does take, so you put current through along a wire and you put a ferrite around it. And as that current flows, you generate a magnetic flux in that ferrous material, which is just a magnetic field and it has these field lines. And if the current tries to change suddenly, like a big pulse gets injected, right? It tries to change suddenly. The magnetic flux in the ferrite doesn't want to change. It acts like it's kind of like a spring damper. And it is, in fact, changing the magnetic field variation into heat. A very, very small amount of heat. You wouldn't be able to measure it yourself, but indeed that is what it's converting it to, is it's changing this magnetic flux variation into heat, so that on the other side of the ferrite you don't see the current pulse. You only see it on the input side, not the output side. And so there's this interrelation of changing energy states. Yeah.
So a shunt would be more or less like a pressure relief valve. A
Yeah.
ferrite would be more like a filter that is grabbing all that excess and dialing it down to what it's supposed to be by suppressing a bit of that energy, like you said, as heat. And then the traps. How do the traps
So those
particularly?
are very similar to the DEF CON, except they use a different device in them. The DEF CON uses metal oxide varistors, which are very standard, heavy-duty, high current shunting devices. The traps, all the trap products use a transient voltage suppressing diode, a TVS diode it's called. And the advantage of those is they're super fast. They turn on in a few picoseconds. And so they're plenty fast enough to turn on for E1. They don't have a lot of people, the big question I had when I first came out with the track is, how could something so small protect against an EMP? It doesn't make any sense. All right, what are you talking about? But I actually did a YouTube video where I calculate out how much energy it is. And the reason the EMP is so harmful is not that it's a ton of energy, it's that it's a small energy in a very, very tiny amount of time. All right, and so it looks like a ton of energy because it occurs in such a brief amount of time. And as long as you have enough capacity in the device that turns on to handle that very brief pulse, that E1 pulse, which is about zero point 0.1 joules per square meter. It doesn't sound like a lot of energy, but again, it happens in nanoseconds. As long as you can turn it on fast enough, you can shunt that energy away. And indeed it does. I've showed the calculations, show that it works, and I do a little demo and stuff of how it works. But so the idea is to have devices that are fast enough to turn on for E1, and these traps, that's the idea of the traps, and devices that are robust enough to handle all of the energy that might be introduced over E1 and E2, and that's like the DEF CON, for example. But there are different parts in them, there's different components, but they have very similar functions. They're both trying to shunt energy away.
Right. And so what we're really trying to bring home, because we did get a lot of mixed signals on the comments for our EMP video, which I did my homework and I watched a lot of your videos on how this system works prior to doing the video and doing all my installations and having conversations with the staff at each company and just kind of getting a real good basis of how everything works. And obviously everything is not 100% tested because we haven't had an event that we could test 100%. And I know I've heard you had conversations before that in order to do these tests, it costs close to $10,000 to actually do a test like this. So the amount of expense that it takes to actually do full testing is pretty high. And so what we're trying to do is essentially mitigate those by putting these insurance devices on our vehicles.
Yeah.
And I have been in situations where natural disasters have happened. We're in Colorado, so we get heavy snowstorms. We're a very dry area. We've had fires as well as mudslides thereafter, where I've gotten trapped for 12 hours outside of being able to get home. There were certain routes that we could take, so that's one thing that we try to emphasize when it comes to upgrading your vehicle. would be making sure that if your vehicle is able to be mobile to go to some of these more uncared for, unmaintained roads to get home, sometimes that's your only option, especially in cases that we have living in our valleys that we do. And so it's one of those things that when you add these layers of protection to mobility, then you're just giving yourself another opportunity to be able to get home to your family, to reconvene with those people that you're trying, your loved ones, the people that you care about, or in some cases you're able or mobile enough to go help those in need, as people with first aid or first responder training to actually get there and help those that need your help.
Sure. Yeah.
Kind of switching gears a little bit and going into not just mobility for vehicles, but also home and building protection. So obviously we want to make sure that we can get home, but if we get home and we have devices in our home that kind of help us stay at least somewhat applicable to the modern devices, whether that's keeping phones charged, radios charged, whatever. So it might be a generator, it might be just your home electronics. Maybe you need a refrigerator to stay up and running for insulin, those kinds of things. Can you speak to some of the devices that's used for home? And in my particular case, I also have a solar array as well.
Yeah, so to me, I think of the home protection kind of as two pieces. The first is you'd like to protect your stuff, right? Your computers and your refrigerator and things that you've come to rely on that make life a whole lot easier, right? So that's one thing. How do I protect my stuff in my house? And the second is, how do I have power to operate if the grid goes down for a long period of time, right? And both of those are events that could, you could definitely damage stuff from an EMP or CME, and you could definitely lose power for a long period of time from either one of those as well. One without the other doesn't do you any good. If you have power but you got nothing to power that's working, it really doesn't help you much, and vice versa, right? And so I try and think of both of them. And so in terms of protecting your stuff, your house, it's a fairly straightforward thing. Again, you can't shield your house very well because it'd be a pretty big blanket, right? So you have to say, all right, what's the biggest threat to my house? And the biggest threat is the power line that comes into my house is going to bring in a lot of unwanted energy when an EMP or a CME happens. And so what I'm going to try and do is, at least I know where it's coming. It's coming in the pipe of my power wires. And so you can put a good Type 2 surge protection device at the main breaker panel, all right? I recommend one. I like the Siemens FS140. I don't have any relation with Siemens. That's what's on my house. I took apart every one I could find, every surge protector I could find, and it was the best one, period. All right. So doesn't matter whichever one you ask me, I probably looked at it and I like the Siemens better. So I recommend that product. And then the other thing you can do is you can add some very special ferrites around the incoming power wires. All right. Now, if you just clip a normal ferrite, again, like one like this, the problem with them is they're really only designed to have about an amp or two of current flowing through the wire, and then that magnetic flux that goes through it kind of fills it up. It gets saturated like a sponge. All right, a sponge, eventually you get enough water and you can't mop up any more water, right? But if you introduce a very small gap in the ferrite, and I mean you have to control it to within a thousandth of an inch, you can greatly increase the amount of current that can flow through that wire and still get a lot of protection. People have known about this. It's not like I imagined it. People have known about it for many, many years. But it's difficult to do on a low-cost way. But we came up with a way to do that. It does a great job. We essentially create these special ferrites. They're called high-saturation ferrites. Just means they take a lot more current to saturate. You probably got one there. Okay, yeah, exactly. Yeah, so it's a ferrite that we've modified by introducing a very precisely controlled gap in the ferrous material using polyimide. And so anyway, you want to put one of those on each of the lines, the two hot lines and the neutral line. You can also put a ferrite, a broadband, a regular ferrite on the ground line as well. And that at least try and prevent some fast transient currents from coming in your power wires. If the energy gets high enough voltage, the surge protector turns on, boom, takes the energy away before your house is blown up, right? It's also helpful for lightning. That's why surge protectors were mostly invented, was lightning protection. So it gives you a double protection there. And for a house, that's the main things. You can certainly go into the house and use ferrites on individual power cords as well. That's great because, of course, energy is going to couple into the house wires directly. So you can clip them on the power wires. The rule of thumb is always put the ferrite as close to what you're trying to protect as possible. All right. So if I got a computer And you say, well, which end of the power cord do I put the ferrite on? You put it at the end close to the computer because that's what you're trying to protect, right? So you can use small ferrites throughout the house as well. And then if you have some things in the home that are never plugged in, they're just freestanding, you just use them on occasion, you can store those in Faraday bags are probably the easiest. I brought one here. This is a Faraday bag. They do great. They're insulated, metal bags that, it's my opinion, anything you put in one of those bags is going to survive because it's just so much shielding, all right? So those are kind of the methods. You can shield individual things, you can put ferrites on power cords, and you can go to the breaker panel and put special ferrites, high saturation ferrites, and this big surge protector at one of the breakers. And that does a pretty good job of protecting your home from transients. Now, does it mean that nothing will be damaged if an EMP occurs? No, it doesn't mean that. You could have a very sensitive computer or a radio system with an antenna that's poking up above your roof. Well, that antenna is just saying, what's its job? Bring in electromagnetic energy. That's what its job is. It's going to bring in the EMP energy if it's in band, and it probably will be. And then the radio's job is to listen for the smallest whispers of EMP energy and somehow make sense of it, right? Amplify it, make sense of it. Well, guess what? The EMP is a gigantic noise that's going to come in and probably damage the radio. All right. That could happen regardless, but you can still take steps to try and buy that down. You can use an antenna disconnect, for example, so your antenna is not connected to your transceiver. You can use a surge protector that your radio is plugged into. I mean, there's all kinds of things you can do to buy down that risk again, right? So home protection is its own thing. Protecting your stuff is what I like to say. And we have a lot of products related to that. And then the other side of it is, well, if I got a bunch of stuff that works, but I don't have any power, I'm probably still going to be in trouble, right? And so you've got the idea, I think, which is the best idea of the two. There's sort of two options. You can use a generator, fuel burning generator of some sort, or you can use a solar power generation system, right? The beauty of solar power generation system is you don't have consumable fuel that you will run out of very quickly. You can't store very much fuel legally. And then there's a fire hazard and all that stuff, okay? So there's all kind of regulations against storing too much, and if you burn your house down, your insurance company won't pay for your house. So just everybody be very careful about overstoring fuel, okay? But a solar thing's beautiful because you don't have to store the fuel. You can have a solar power generation. Even if you're not getting enough energy to power the whole house, you can power some things, right? You can harden it as well. So you can use ferrites and you can use protective surge protectors. You can try and get your solar power generation system hardened. And truth be told, your solar power generation system would probably survive. All right, it probably would. Panels are pretty darn robust. Your weakest points are probably your inverters. And as long as you have a surge protector and some ferrites, you probably would survive. All right. So that would give you a lot, right? Now you've got the ability to bring energy in. And like you said, if your elderly neighbor over there, needs help, you have the ability to provide assistance to others to some degree. So I think it's great having a secondary power source. If you can't afford solar, or you're in an area where it's not allowed or whatever, you can try and have a generator, and it's better, by far better than nothing, for sure. I have a generator in my house. I don't have solar. And my generator is with natural gas, and so when we lose power, natural gas flows, it kicks on, provides house power, and it's wonderful. I love our generator. But in a long-term blackout, eventually the utility company providing my natural gas will also go down, right? Eventually its systems will go down, and I will lose that natural gas source, and then I'd be in trouble. So I don't know that it's as good as a solar solution, but it's hands and feet above, no protection. And so those are kind of your options. And you, of course, can have a portable generator. If you don't, I have a whole house generator, but you can have a portable generator. You can have some of these small units that you can, just use to recharge things. For example, I have one of those for recharging cell phones and radios and things that are kind of critical items. So lots of ways you can do it, but I like to think about a power source and then protecting my equipment. That's kind of how I divide it.
Yeah, I have a manual transfer switch for our home for this small solar generator that we have. So we calculated that approximately 36 hours of just running our heat circuit for our boiler, and so at a full charge, so that we can, at least in the wintertime, stay warm if the power happens to go out. Now, I'm eventually looking for longer term solution to pull that 36 hours into, hopefully days, weeks, which would be great. Because like you said, if you're running off of gas, that gas eventually does stop if the generation of that gas is not getting power as well.
Right.
So there are certain contingencies that you have to kind of think about, whether it's short term or long term. And unfortunately, it seems like based on a lot of comments, people don't think that far ahead past a certain point. A lot of people say, well, if your EMP hits your vehicle and you're the only one driving, then good luck getting through roads and this and that. But again, it goes back to mobility. If you have a vehicle that is capable of hitting camp trails and roads and things like that, then you have no problem hitting the median and just driving a shoulder for miles until you can get past a jam of traffic. Um, if you work in the city and you live in the suburbs or rural area, you're going to want to get home and you're going to have to traverse over curbs, over many different things that you try to get over. And so sometimes having a little bit of lift and a larger tire will help you get through that situation. And even if the gas stations are down, being a mechanic, pretty much all fuel tanks these days are all plastic. It's really easy to get fuel out of a plastic tank.
Sure.
Because siphoning doesn't really work anymore because of
Right, right.
the vacuum systems with gas tanks.
Yeah, yeah. It's funny you say that because in one of my books I wrote a series called The Survivalist. I don't know if you're familiar with it, but it's a 12-book adventure series about a post-pandemic. And that's one of the first things he does is he goes to abandoned cars and drains the gas tanks to try and keep himself fueled up as he travels across the country. So yeah, absolutely right. One thing I'll point out about EMP and vehicles too, since I know that's a focus of yours, it could well be that a person is driving down the road and an EMP event occurs. Now, keep in mind, you're not going to hear it. You're likely not going to see it, okay, because it's so far up in the atmosphere, right? It's maybe 300 miles up, all right? So this thing's going to detonate, and unless it's nighttime, you're not even going to see a flash or anything. It's just things might just stop working, right? Think your car just stops and stalls, and other cars are stalling. In an event where multiple things are happening around you on a road like that, it might be an indication of an electromagnetic event, right? You would want to steer safely off the road, of course, and even if your car has died, it may well be possible for you to restart it. It could be that your car has just shut down and it's able to be cleared and restarted. So I always tell people, get to safety, shut it off, restart it, see if it'll restart. If it won't, it may be worth trying to disconnect the battery, reconnect to kind of clear it as best you can. I know not all cars you can do that with, but some you can. And you can clear it, reconnect it, and it may then come back up because you may just be in a fault state in the vehicle. And so it could be, you have a little bit of room there to maybe recover. Don't give up right away on the vehicle. Spend a little bit of time seeing if you can get it going. Because I'm in your opinion, is having wheels and some mobility is, might make the difference of surviving this event or not surviving this event, because it gives you the way of navigating yourself back home, where at least a lot of people say, I'm going to bug out. Well, an EMP is an event that's difficult to bug out from because it may have affected large regions of the country, and you have no idea which way to go until you sort of assess the situation, right? Your best bet is to be back at your home base where you have all these supplies all around you, right? You have a whole house full of supplies, and then figure out, where do I need to go, and where do I go, and how do I get there, right? That kind of,
Yeah.
yeah.
Well, that's one thing, part of my contingency is that I do have one of your Faraday bags with a ham radio in it. And I haven't yet programmed all of the repeaters locally to my area, but if you had to, you still have to grab that radio or whatever that you may be able to, because you're not sure what's going on, and you have to get to higher ground so that you can get better line of sight depending on kind of the radio that you have, so that you can kind of figure out what's going on. You can hear the chatter of what's going on through radios, more information that people have. Because if your cell phone works, if the TV doesn't work, if the internet doesn't work, how are you going to find information to know, okay, this area is affected, but the area that's not affected that people can evac to or whatever is in this location. So being able to bring up communications, which I have a lot of family that's in the military, is paramount to your next step once you've kind of got home, got to your safe place, and got out of the chaos in order to actually think straight so that you can kind of figure out how to keep your family safe and what's your next move.
Right. Yeah, I agree.
I did have a question. Is there anything that they have for smaller mobility devices like e-bikes or scooters, or anything that can protect those kinds of?
I have not looked at them carefully to see, what you could do to harden them explicitly. My first thought is I would cover them. Right, I would have some kind of like a motorcycle style cover that was made out of conductive material, and again, that would all but guarantee their survival. The only disadvantage, there's two disadvantages to that. One is you can't drive the thing when you've got your cover on, right? So you're not protected when you're moving. And the other is that covers are very expensive. The material is just crazy expensive. So a cover for like an e-bike might be, I don't know, $800 or something like that for a conductive cover. And many people would say, well, that's just not, that's too much money to spend on buying down this risk. So I don't know if there's a reasonable way to use like transient protection devices or ferrites on like an e-bike or a scooter. So I'd have to look at that more.
What about EVs? Do EVs have any chance of getting through this? Because I know
I hope so.
you
I
can't
have
you can't
one.
do so much on them.
Yeah, I have an electric vehicle now, a Ford Mach E, and so I'm familiar with the general ideas of them now. And the short of it is they have two different electrical systems, right? They have a 12-volt conventional battery system, which you could protect just like any other vehicle, and you should. But then they also have this high voltage lithium battery system that's not in any way for you to mess with. You don't want to get in there and mess with that high voltage lithium battery system. And how susceptible is it to an EMP? I have no idea. All right, I don't know. If it is very sensitive to it, then you're going to be in trouble because you can't really get in there and mess with it and protect it. Now, I did have the idea recently. Now, of course, you can still cover the car, right? When it's not unplugged, you can cover the car, and it's just like any other car, you can protect it. But some of the time, you're going to be plugged into your power grid, right? Recharging. I'm often plugged in at home. So I did have the idea. A very useful product would be a transient protection device that goes between the plug of your cord and the plug on the car. You intercept it there and drain it to some sort of ground. So that's something I'm going to look at, but I'm not aware of anything like that now that exists. So the short answer is I think it's more risky. I think EVs are riskier and more susceptible than a combustion burning, a regular car. But I don't know how much more. I'm not really sure yet. And maybe there's some steps we can take to protect them.
So maybe in terms of a spectrum or scale, your pre-1990 cars are pretty robust to anything prior to fuel injection, and then everything that's modern for the most part is going to need some type of device to it. Hybrids you could probably do something with because it is still a hybrid motor that you could protect, and then EVs are kind of at the further end of the spectrum that we don't have a whole lot for at this point.
Yeah, and we don't have a lot of data either. I mean, I have read there are built-in surge protection devices in EVs, in electric vehicles. And that makes sense, of course, because you're going to get surges on your power lines, right? And you don't want to damage this expensive battery system. So I suspect that is true. The question is, how robust are they, and are they meant to withstand, really big events? I just don't know. So I think you'd have to have some further study, and even the study on regular gas-burning vehicles has been very, very limited. The EMP Commission did a study, but it has all kinds of problems people have pointed out with the study that was done. So the only takeaway people came away with was, yeah, you can damage cars with an EMP. I'd say take that away, but anything above and beyond that was kind of in question. What percentage of vehicles, what's most important, what kinds are most susceptible, least susceptible? I think the only takeaway is, yes, they can be damaged, which of course that makes sense. They have all kind of modern electronics in them, right? And then again, to protect them, you have your choice. You can cover it up with something conductive, or you can try and put in as many of these transient protection devices as you can.
So, you spoke about the EMP Commission, but I know that a lot of the different companies that make devices are also offering these devices and installing these devices on first responder, municipal, state, and government agencies for their vehicles, because obviously they need to stay mobile and able to do their job still. And so can you talk about some of the testing that's involved in order to make sure that these devices are up to snuff for these regulations or licenses or whatever that needs to be?
Yeah, no, it's a great question, and so I'll give you a corollary. When we field satellites in NASA, right? We build the satellites with lots of ideas in mind of how it's going to survive different events, and then we take them into electromagnetic chambers, and we run a series of tests on them. Mil standard 461 tests, pulse tests, all kinds of tests on them, right? And then we're confident that under those environments, this thing will operate, right? And then we fly it. And so many satellites would survive an EMP. It's part of 461 testing now, right? And so we go to that expense in NASA. In the space industry, that cost is so small compared to the cost of putting something into space or developing something. Of course you do it. With cars, though, or any other small-scale electronics, it's very expensive to test. and there's a lot of misunderstanding about what is being tested. All right, so let's just give you an example. Let's say I've got this DEF CON, right? And it's a heavy duty, like really nice product. If I take that and I test it versus an EMP, I am 100.0% sure it would survive. Okay? How am I sure? Well, an EMP can't introduce enough energy to damage all those transient parts in there. There's no possibility it could. I am 100% sure, though, that this one would survive an EMP. I am 100% sure that this would survive an EMP. I'm 100% sure, not even slightly unsure. In fact, I'm 100% sure that many things that don't have complex electronics would survive, let alone anything designed to turn on at high voltages, right? But it doesn't prove anything. Just because my DEF CON survives doesn't mean your car is going to survive, right? I'm not testing your car. Now, if I run a test on this product and I say it's EMP tested and it survives, the value of that is small. Okay, there's not a lot of value of that because you should expect that. Okay, if it didn't survive, we built a bad product. Okay, the bigger question is if I hook that to my car and I take my car into the EMP chamber, will my car survive? Right now, if I show that, all good. Okay, now I've accomplished the mission and the goal. With just like the satellite, we take the satellite into the room, right? And that is very expensive and just not done, frankly. The EMP Commission did a little bit of that, but what they did is even they were worried about the cost of damage to the cars, so they only dialed up the pulse until they started seeing anomalies, and they said, whoa, dial it back down. That one's going to have susceptibility. They didn't go hit it full scale, let's see if it breaks, all right, because they didn't want to damage a bunch of cars. So what I tell people is, yes, it's good to have things tested to mil standards, individual products. Mil standard 461 or 464 or 2882, sure, you can do it. 18125-1, you can test them and you can be confident that somebody didn't do something stupid and put like a really sensitive piece of equipment in there. But it does not guarantee that your product will be protected, okay? So what you really want to do is see real world tests of this thing attached to something and then that something tested, okay? I hope we get there, all right? It's just such an expensive process, people don't do it right now. Now, I'm very fortunate, I may have a way soon to at least do small scale testing of true EMP energy on devices, not just protective devices, but full up systems. And that would be great because it'd be nice to have some videos of, hey, we're going to put this laptop in here and we're going to attach this protective system and bang, we hit it with an EMP and it's still working just fine, right? That tells me something. Now, there has been some of that done, to be fair. The only company I know who ever did it is a company that makes solar energy inverters and solar energy systems. Everybody would know them if they search EMP solar, they'll find them. They actually bought their own EMP generation system, is my understanding, and they started zapping their systems to find out where they broke. And indeed they found, whoop, this broke, we got to add more ferrites here, we got to do this here, and they could get systems that would survive an EMP. So that, hats off, right, to that. That's great. But other people who market things as EMP products who have been tested, they're really just testing their products. So be sure you understand that when you buy them. It's not a negative, but it's not the full up, all is good. Okay, so they need to take that one step further. The perfect test, of course, would be I take a vehicle, I roll it into the chamber, I zap it with an EMP, and it is damaged. I slide it back out, I replace the defective components, I attach protective devices, I roll it back in the thing, I zap it with an EMP, and it is not damaged. Same vehicle, all I've done is add the protection. Then you could be confident, my protection really does save my car, right? But you can imagine...
Just that particular car.
Just that particular car, right. And you can imagine, well, yeah, but that's a Ford F-150. I've got a Chevrolet whatever, right? And so maybe they're not quite the same. And you can understand the complexities and difficulty of that. But all that aside, tested products are better than non-tested in terms of just having data, so I'm good for that. And we should just look to advance the testing further, where we can start demonstrating systems or at least subsystems that show that you've protected them. All right, that's my pitch on it.
I guess to just land the whole conversation here as we get to the top of the hour, we're really just talking about insurance of your mind being able to get to the next step. If you've ever been in a crisis situation or a situation seen a car accident and something, your mind immediately goes into these certain inoculated stress points, and your ability to think to the next step is obviously very paramount. And being able to have a vehicle, in this case, to get home. If you're 20 miles away from home, it's going to take you probably all day, if you're at a good pace, to get there, to get home. Probably 12 hours to walk your way home, as opposed to 20 miles traversing at 15 to 30 miles an hour, having to get through things, through jams, whatever, to get home, to get to your home base is really important. And so we're not trying to say that everything that's out there right now in the ether for devices is a 100% guarantee, but there's a reason why we put locks on our doors in our houses. There's a reason why we get a guard dog. There's a reason why we get an alarm system on our house. These are all contingencies for essentially our ability to be prepared for the situation. And instead of walking into a construction site with a hammer, you have your hammer, you have your tools, you have this tool for that tool. And so having an array of tools to be able to prepare you for a situation that you are hopefully prepared for as best as you can is really the objective.
Right, right. Yeah, and I looked at preparedness. I'm not just in EMP preparedness, but in preparedness as a whole, right? I've been involved in this community a long time, and I have a handbook out. You can talk about it, or show it to customers if you want, but there's a big handbook I wrote when I first got in the community, where I looked exactly what you're saying. I tried to look at all the different kind of threats we might face, and I tried to, I read every preparedness book was out on the market, and I tried to sort of boil it down to what I thought was most important, what worked, and I wrote this handbook to practical disaster preparedness. And that's kind of what you're talking about, is putting in place layers of protection so that you can kind of get through. Maybe it's not an EMP this week, maybe it's a solar CME, or maybe it's a giant snowstorm, or maybe it's a biological attack, or maybe it's a cyber attack on our hospital. There's a lot of different things that can affect us and our ability to sort of have daily life keep going. And having a really good preparedness plan, I think, is critical to everybody. And so I would encourage people, think beyond EMP, but think about preparedness as a whole, and EMP is a portion of that. It is one of the threats that you might face. And what you find is a lot of your preparations overlap. Right? You still need food and water and power and other things for all of these things, and some are impacted, some are not, based on different threats. But kind of create an overall preparedness plan, and that's what I talk about in the handbook. And then EMP falls into that. I mean, it's part of it. So that's kind of my thinking.
Well, there's a few books that, if I can call you, the doc here has.
Sure.
And so this was a good reading list if you guys are looking for some more books on the subject. There's Disaster Preparedness for EMP Attacks and Solar Storms, Prepper's Instruction Manual, 50 Steps to Prepare for Any Disaster, and Handbook for Practical Disaster Preparedness for the Family. All of them available at watchmanpress.com, and you can use code PREPPER, all caps 2024, and save 20% on all his books there. You can also go to disasterprepare.com and use discount code PREPARED23 on either there or Faraday Defense. For all of these devices to get a discount there as well. So we wanted to thank you again, Doctor, for coming in and talking to us and giving some education to all of these questions that surround the internet around these devices and how to protect ourselves. Any last words you'd like to tell?
No, I appreciate you having me on. Hopefully it was helpful.
Be sure to like and subscribe if this video brought you some value, and check out our website if you guys are looking for any off-road tires and overland tires at pitstopoverland.com.